get back to where I was here. All right. Hello, everybody. Want to thank you all for coming to my Epic Week talk. I've been super excited for quite a while to present my talk here. So without further ado, I will go forward. So, as you all know, I spent 2 years teaching an AI to generate music, and I wanted to show you all what happened. This is very exciting. So, before I jump right into this talk, I'm going to kind of walk through the agenda a little bit, sort of a broad overview of what I'm going to be talking about. First, I'm going to set the scene a little bit, talk about the major players in this project. Then I'm going to give some background on why exactly I did this. And then we're going to jump into the meat of the whole thing and how do you make AI generated music. After I teach you guys how to do that, we're going to look at what happened, what were my results, how did this all go, and if we have some extra time, I have some additional material in the appendix and also time for questions maybe. So here goes. So setting the scene. First of all, nice to meet you all. I see some familiar faces, some people maybe not as familiar. That's really cool. I'm so glad you're all here. My name is Josh Miller. I am an engineer on the machine learning models team here at HubSpot. I've been here for about 3 years. I grew up in upstate New York, studied software engineering at RIT. I play the bass guitar, and I am a huge fan of progressive rock and jazz fusion. So as you can see, I'm a bit of a music guy as well as an AI guy. So it kind of makes sense, why I'm doing this. And yeah, I'm a huge fan of AI and generative models. Here you can see a picture of me playing my 6-string bass in a metal band that I used to be in college. And so, maybe I'm the main player in this, but there's a secondary one that I have to talk about in order to make this make sense. And this is my dusty old computer that sits in my bedroom. So here's my computer. I built it in 2016, specifically to do silly machine learning projects. I've got a pretty decent GPU in it, a good amount of RAM, a really weak CPU, and I put a whole bunch of hard drives in this thing. The point here being, this is extremely accessible consumer grade hardware. I don't have any fancy, crazy stuff like Google has. I'm probably like 1 million times slower than one of Google's chips. So this is a big, I guess, part of the setup here. Cool. So why did I do this? That's a good question. So when you look at the world of AI and like AI generated art, a lot of people these days, especially you'll see, will talk about AI generated images. And honestly, they're kind of amazing. You have DALL-E 2 made by OpenAI. This is a text to image generation model. So you basically just type some text in and it will make a picture based on that text. And so you can see this picture over here. They probably said something like, okay, generate a picture of a spaceman riding a horse in space, and there you go. And yeah, this is a diffusion model. I'll get into what that means later, I promise. And it has about 3.5 billion parameters. That is basically one way that we measure the size of these models. It's basically the number of numbers that comprise the model. So it's giant. Also, there are alternatives to DALL-E, tons of them. Here's one that I thought would be worth mentioning. This one's called Midjourney. It's an alternative to DALL-E made by a different company. Once again, text to image, once again, diffusion model. Here you can see over here an example that I found online where they made a rusted iron diesel punk stormtrooper, which I didn't know could even be a thing. So it's pretty impressive. I'd say like the image quality is very high. And I don't know the size of this model, but it's probably a bit smaller than DALL-E, I'm guessing, just because that one's really compute intensive. And then also, I don't know if you guys have seen maybe on like the New York Times, but there is actually an art contest where the winner of the contest actually used AI to generate the art, and it kind of made some waves. So really, like, AI generated images have been really, really good. But in my opinion, AI generated music really hasn't moved as fast as AI generated images in the past almost decade, I'm going to say. So why is that? Well, mostly what people do in this space is they train models to compose music rather than make sounds. And it requires some kind of additional process like MIDI or a human player in order to perform the music. So, they'll train an AI to write the music, but then they need something else to perform it. And so like the AI never really controls the performance or like the true sound of it. They just control almost like the organization and structure of the music. That being said, there are a couple of notable counter examples to this. One is called OpenAI Jukebox. Now, OpenAI Jukebox, I will say, is probably the gold standard for AI generated music, where it just generates sound, but it is very convoluted in structure. It is very, very compute heavy, not something everyone can run. Also, it takes 9 hours for it to generate just a single minute of music. And the final layer of this model alone was trained on 512 GPUs for 2 weeks straight. That's 512 times more compute power than I have. And another example is MP3net, which we're going to be looking kind of a bit closer at later. This is an interesting example, but it was only really tried on a very clean piano data set. But even then, it was trained for 270 hours on a TPU, which is a really expensive AI-specific chip by Google. And the estimated cost of training this model was $2,400. The results, not very good. I think we can do better, right? So the reason why I did this is I wanted to complete a whole bunch of these goals that I set for myself. One, I'm going to make a model that generates raw audio, not composing sheet music. So you can see down here, you see some box sheet music. We're not doing that. We're not writing sheet music. We're making just sounds, and we're going to let the model control just the sound, the raw soundscape. And I'm going to try to apply it and run it on many types of music and maybe even different types of audio in general. And yeah, we're going to try and see how that goes. Also, I want to be able to train and run it on devices that real people could feasibly use. So not a TPU. And honestly, this is a great constraint if I just use my own computer to do it. So I'm not going to be buying or renting any compute to do this. I'm just going to use my old machine. And I'm going to try and produce results, of course, that sound decent. That's a really good goal to have. And lastly, share my results with people. Maybe that's kind of cheating because now I'm doing an Epic Week talk about it. But anyways, so let's jump right into the meat of it. How do you make AI generated music? Well, the first thing that you need when you are trying to make a machine learning model is data. You're going to need a lot of data. So there are a bunch of different choices that we can have for the data set. The first one is the GTZAN data set. I forgot once again to look up what the acronym means. Apologies. But there are 1,000 clips of audio in it. They're split evenly across 10 different genres. So it has 10 genres of music, 100 clips of music per genre, and each of those clips are 30 seconds long. That's pretty cool. It's pretty neat, pretty organized. It's kind of small. If you want to go bigger, you can do something like the Free Music Archive. There are about 100,000 free songs, I think actually a little more. And I will say the production quality is a bit lower, but it also comes with a lot of metadata, and it's into like 161 different genres. I will say there's a pretty uneven split, though. It's mostly electronic music. Alternatively, you can build your own. There are a bunch of different ways you can do that. Be careful there, I guess. But so, okay, now we have a bunch of music data, let's say, from GTZAN. What does the data look like? What does it look like in a computer? How do we use it? So the music data looks like something that I'm going to be calling pulse codes for basically the rest of this talk. And you can think of pulse codes as basically a really, really long list of numbers. What they are really are kind of like air pressure measurements recorded many times per second, usually 44,100 in your standard audio file. I'm not going to go into explaining why, but there's a specific reason for that magic number. But it's kind of tricky to use that when you have this really long sequence of data, that's going to fill up your memory in your computer a lot. But here's a graph right here of kind of the pulse codes. And I'm going to show you guys a clip of what these pulse codes sound like. This is Jazz Clip 0 from the GTZAN dataset. And we're going to get kind of familiar with this one as we continue. So this is what I'd like to call a one-dimensional representation of the data, because it's basically a long, flat list of numbers that we can plot over time. But what if there's a different way that we can use it? Well, another thing that we can do is we can make a spectrogram. A spectrogram is kind of like a 2D representation of the data. And it's sort of analogous to an image that way. Basically, what you're going to have on the x-axis is time, on the y-axis is pitch, and on the z-axis, which we're going to represent with color, you're going to have loudness, how much of that pitch is present at that specific time. It's nice because it's two-dimensional, and we can take basically some of the concepts that we use when we generate images in AI, and we can use those for music as well if we can generate a spectrogram, which is kind of where this is going. And yeah, what's cool about a spectrogram is if you are careful and you're clever about it, you can convert it perfectly back into audio, those pulse codes, that flat thing that we looked at earlier. Alternatively, if there's a different kind of spectrogram called a MEL spectrogram, and this one is, the same kind of concept. X-axis is time, y-axis is pitch, z-axis is color, which is how loud that pitch is at that certain time. But this time it warps the y-axis in order to match the human perception, how we hear pitches. It does look like a bit sharper and cleaner, and we're going to see that in the next slide, I promise. And maybe because of that, it might be easier to generate. But that's mostly conjecture on my side. And the tricky thing with the MEL spectrograms is we really don't have a good way to convert it back to pulse codes, which is kind of unfortunate. So here are the spectrograms. I don't know why the normal one went missing here. I apologize for that. But I'm going to at least show you the MEL spectrogram and see what that looks like. Once again, here's the audio clip. And so once again, the x-axis is time, the y-axis is pitch, and the z-axis, the color, is how much of that is present. Now I'm going to play this again, and I'm going to sort of walk you through things that I'm hearing in the spectrogram. So you can hear that first kind of trumpet swell. It calms down. The piano is kind of moving around a bit. Then you can hear the trumpet climb back up, and it sits on that long note. And you can sort of see that there, which is kind of cool. Now, what you would have seen in the normal spectrogram, I'm really not sure why it's not showing up here, but it looks a lot grainier. And this middle part is actually kind of squished down. It's really hard to see. So that's kind of the difference. There it is. It's back, guys. All right. Cool. So now that we know about spectrograms and how that's going to be our data representation for the model, here is the full kind of thing. Here's what it's going to look like. So we're going to start with the audio training data. And then we're going to use some spectrogram function to convert the training data back to into spectrograms. So we're going to take the pulse codes, turn it into spectrograms. And then once we have all of these spectrograms of our data set, we're going to train a machine learning model to look at those spectrograms and learn how to create new ones. Once the model gets really good at that, we're going to tell it to generate some spectrograms. We're going to run our inverse spectrogram function to turn it back into pulse codes, and then we'll have brand new music, and that's what we're going to use. Now, you're probably wondering, what does the AI square mean? What are we actually doing there? And that's what I'm going to get into next, because that's probably the most important part. So I ended up trying a whole bunch of different options, but I'm going to look at two in this talk. So training option number one is something called a generative adversarial network, known in the industry as a GAN. And basically what you do with a GAN is you make two neural networks fight each other. One tries to generate fake music, and the other one tries to tell what music is fake and what music is real. And what's great about this is you only need to give it real music. And as both of these neural networks get better, the music gets better. So here's kind of how it works. You take some random noise, and then you're going to feed it into your generator model. And that generator model is going to make fake spectrograms from it, kind of like this one. And then you're going to take those fake spectrograms and some real ones, like the ones that we saw earlier, and you're going to give that to our second neural network, the discriminator. And it's, without telling it which one is fake or real, it's going to try to guess. And they're both going to be very bad at their jobs in the beginning. But you're going to train them. Basically, you're going to reward the generator for tricking the discriminator, and you're going to reward the discriminator for calling out the generator on being fake. And you can keep looping this for a while. It creates a feedback loop. And that's kind of how that works. The other alternative, training option number two, is something that I've alluded to earlier. It's called the diffusion model. And in order to describe this, I'm going to use an analogy based on a quote by our boy himself, Michelangelo. Every block of stone has a statue inside it, and it is the task of the sculptor to discover it. Basically, you can think of diffusion models as the same way, but I'm going to change it up a little bit. Every block of Gaussian noise, that's this TV static looking stuff, has music, or in this case of this picture down here, an image of a dog inside it. And it's the task of the neural network to discover it. And that's probably what he might have said if he tried doing this project as well. Basically, what you do is you are teaching the model to learn to denoise noisy versions of data. So you're going to give the model, let's say, if you want to generate pictures of dogs, you would give it this noisy picture of a dog, and you would say, what noise was added to this picture of the dog? And the model is going to have to learn that. You can do this for incremental steps, small amounts of noise, added, until you get all the way to the noisy bit. Once the model gets really good at that, what you can do now is you can take an advantage of that system, and you can start with completely random noise, which is trivial to generate. And then you can say, okay, refine this into the image that it used to be when it really wasn't to begin with. And from there, you're going to be able to generate, in this case, a picture of a dog. But in the case of our model, you're going to generate a spectrogram. And that's what we're going to use to create music. So here's an example of that actually with a spectrogram. So you can see, okay, here's our noise. And we've trained a model to do the diffusion function already. And all right, so we're going to take a step and remove some of the noise. And you can see some signal coming through. And then you're going to do it again. We're going to see a little more. And then later on, you're going to get this one with, like, you know, kind of really bright peaks. It looks like a spectrogram. This is really cool. And I think this GIF is very pretty and mesmerizing. I had to include it. Okay, so how do we end up generating music from the trained model? The nice thing is, with both of these architecture, generating the music works the same way. You take some random noise, you give it to the model, and it spits out a spectrogram that it has generated and thinks it will be real music. All you have to do then is take your inverse spectrogram function, turn it back into pulse codes, and then plug in your headphones, and you're ready to go. So now we're going to move on to the results section. What happened with this model? Now I'm going to give a little bit of a content warning here. There are going to be some loud, harsh sounds ahead. I'm going to warn every time before I play the music. I have adjusted the volumes, and I've tested this, and I haven't gotten any major complaints, so we should probably be fine. But, you know, feel free to yell at me in the comments or something. So the first thing that I did is I wanted to replicate MP3net, which I forgot to mention before. MP3net is a GAN model, generative adversarial network. It's that first training option number one that we saw before. Now, before I play this clip, I'm going to say immediately, this one's not great. It sounds like you took most of the training data and you averaged it together. The loudest track in the data set seems to be the one that reliably pops through every time I've tried training this model. In this example that I'm about to play, it is from training on the blues section of the GTZAN data set. So I'm going to start the music right now. 3, 2, 1, go. And honestly, if you didn't know that that was in the data set, it would be cool to think, oh, wow, that was really good. But it's literally copying the data set. And that's no good. We want to generate new stuff, not crappier versions of the stuff that we trained on. So not too good on that front. So then I thought, okay, well, I tried that for a while, and now I'm going to switch to a diffusion model. Now this one gets a little better. And it gets even better with training over time, which we're going to see with these two examples here. We might actually have something here. Now you're going to see these spectrograms. These are kind of the normal type of spectrogram. And that's what I started using with the diffusion model. So here is what it looks like after 1 hour training. I'm going to play again. 3, 2, 1, go. And so that one sounds kind of wonky, right? But I'm going to play it again and listen very carefully. You're going to start hearing some things that kind of sound like guitar plucking if you listen closely, like an acoustic guitar. And so that's kind of interesting. So I kept training it for a little longer. And this is what I ended up getting. All right. 1, 2, 3. Now that's interesting because that didn't sound like anything in the data set. It had a clear beat. This was trained, on GTZAN blues. I would say that that sounded pretty bluesy, and it was kind of moving along there. I would give that one a pass. And this was kind of my aha moment. This is where I was like, oh, shoot, those diffusion models, they really do work better. No more GANs for me. I'm doing diffusion only from now on. So after seeing that with blues, I was like, all right, let's try this on other genres. Let's see what happens. And so I've got some more example for you guys. If you remember from my intro slide, I said I like jazz and metal, and that definitely seems represented here. So we're going to look at the jazz genre of GTZAN. Now, for each of these, I've given you a little bit of like flavor text of things to listen to, listen for in these clips. So for this one, try to listen for like horns and brass, maybe upright bass, and you can almost hear something that's trying to be vocals, trying being the operative word here. And here goes. 1, 2, 3. So, not great, but we did hear some bits of like jazzy sounding stuff in there. Now, next one, this one's going to be kind of intense. This is the metal one. What you're going to listen for in this one is like intense guitar riffs, various metal vocal sounds, I will say. There's kind of like a drum pause sort of breakdown thing in there, and there's kind of a scream, which is interesting and cool. So yeah, here goes with the metal sample. 3, 2, 1. Drop some horns emojis in the chat. But yeah. And then so the next is reggae. Now this reggae one, I'm going to say it was one of the genres that performed the worst on, and that's part of why I wanted to include it in here. So this one, you're going to hear like a reggae beat. You're going to hear some like kind of chorus vocals in there that kind of seem reminiscent of reggae as well, which is kind of interesting. And so we're going to go with that one. 3, 2, 1. Here we go. These are chorus vocals I was talking about. So, it sounds kind of like wobbly and wonky, but there was some like interesting sound to it. So then I was like, all right, it seemed to work fairly well on the small data set. Can we scale it up? Can we scale it up to larger data sets? And I decided, as a metal fan, wouldn't it be cool if I took Metallica's first 4 albums and training on that? And what I ended up doing was making my own AI generated Metallica album by training on the first 4 albums. I'll include a SoundCloud link later. It's in the slides. And so some things you'll want to listen for in this. Vocals that do sound like the singer of Metallica. If you've listened to them before, you'll recognize it. If not, it's okay. You'll hear it. There is also like a similar guitar tone to what Metallica used in their early days. And you're going to hear like a double bass drum kind of technique, which is pretty popular in this style of metal as well. But I will say it sounds like the drummer has a few more feet than a human does sometimes. Anyways, here we go. 3, 2, 1. Now it's kind of harsh and unrelenting, but you do get some musical textures which are very clearly reminiscent of early Metallica, which is really fascinating. So then I decided to switch to a different audio representation. Now, as you remember, I was using these old kinds of spectrograms because I knew how to invert those and turn them back into audio. But with the MEL spectrogram, the cleaner one, I wasn't really sure how to, until one fateful day in August, I happened to see some similar research by a man named Curtis Hawthorne, who is on basically the art branch of Google's AI team called Magenta. And I was telling him, hey, why did you use a MEL spectrogram? Isn't that hard to invert? I used this other thing. And he's like, yeah, I tried to use the thing you used too, but it wasn't good enough. So I trained a model that inverts. I trained an AI model that turns the MEL spectrograms back in the audio, and using that was a lot better. So I was like, wow, that's really cool. So he ended up sharing that model with me. It's open to everyone on TensorFlow Hub. And now that I have that model, I can happily work with these MEL spectrograms, which look a bit cleaner, and invert them for free. So that's great. I can turn them back into audio. Since that opened things up, I decided, okay, hey, you know what? We're going to try and generate music and now types of audio with the MEL spectrogram. You'll see here I have 4 different samples. I'm going to be looking at a jazz fusion band, and then a pop band, and then the Beatles, who you may have heard of before. And then I decided it would be really cool if I took a bunch of audio from my brother's YouTube Let's Play videos, where he like plays video games, records on YouTube, and basically talks over it. I'm going to try and generate his voice, because I have actually about 50 hours of that audio data. And so that's what I did. We're going to look at these. We're going to look at the real data and then generate it and kind of compare them for each of those. So first up is Cassiopeia. They're a jazz fusion band. They're from Japan. I think they're from like the 70s or something. But I learned about them recently through my YouTube recommendations, and they're pretty cool. So here's a real example of some of their music. It's kind of chill. You have the slap bass. You have kind of dreamy sounding synth, a little bit of guitar in there, shuffling drums. Can't say enough good things about the synth. It just sounds great to me. All right, so then we're going to look at some generated sample that I trained on this data. And so here we go. 1, 2, 3, generated jazz. Now it's not super structured, you can tell, and it kind of explodes every once in a while. But you're getting a lot of musical textures. You're getting that synth. You're getting like the drums and stuff. And what's really interesting is actually learning some of those like jazz lines. Where it's like It's like it's getting that, which is really interesting. I didn't think it would be able to pick up on something so subtle like that. But pretty cool. It seems to like get the musical textures of the source material pretty well, but I'll say the structure is somewhat lacking. Now, next we're going to look at this pop band called Stars. Here's an example of some of their music. Now you can hear the audio quality of this one sounds like crap, and that's on me. That's just my fault. The actual music doesn't sound that bad, I promise. But I downsampled the music for some memory reasons. Now here is a generated example trained on some of that data. Now I'm going to warn, this one like kind of explodes a little bit. So maybe turn down your volume a little bit. But you can hear the gentle synth. You can sort of hear kind of whispery vocals. It's about to explode. Yeah. But yeah, like not too bad. It's not very structured. The words aren't really saying much. Once again, I'd say it's copying the musical textures pretty well, but the like structure is barely existent. Next, we're going to look at the Beatles. Now, I could have picked a well-known Beatles tune, but I randomly sampled for the others, so it's only fair that I randomly sample this one. If you know the name of this Beatles tune, let me know, because I don't. So yeah, some classic Beatles stuff. You can kind of hear them all singing together. You can hear the acoustic guitar, a little bit of drums. Perfect. Now, here is some audio that was generated based on the Beatles. Now, what's interesting is that was Paul singing in the other one, but you can kind of hear what sounds like John popping through in this one, which is interesting. So once again, not perfect. There's a little bit of explodiness. The structure isn't there, but it did pick up on, once again, the musical textures. You can really hear kind of like the vocal styles of, what almost sounds like John Lennon in there, which is pretty cool. Now, lastly, we're going to look at my brother's. Here is some audio from one of his videos.
Uncannily good at it for some reason. Of course, nowadays I'm rusty, but there was one time I'll never forget, and people are probably not going to believe me when I say this.
He's playing Sonic, by the way.
I'm
in case
dead
you're wondering.
serious when I say this. There was one time where I got all 6 Chaos Emeralds purely by accident.
Purely by accident, he says. And so this is some, audio generated based on his speech. Now, I will say I did run this by my mom first, and she also agrees that it sounds like him, but I will leave that up for you to decide. Now, what's interesting is there's like some noises. He does yell like that in his videos sometimes, by the way, so that's kind of accurate. But yeah, it doesn't do like the background video game noises part very well, but it does kind of like get, sort of the textures of his voice. Now it doesn't actually do real words, which would have been kind of spooky anyways, but kind of interesting. And so now we've looked at all those examples, I want to go and take a look back at my goals and ask myself, did I succeed? Can I generate music using just raw audio? Yeah, I can do that. I've designed a whole model and system for doing this. I think I did that part pretty well. Have I applied it to and tried it on a bunch of different genres and types of audio and music? Yeah, I think I did that. And was it able to train and run on devices that real people could feasibly use? Yes, I used my hilariously underpowered dusty old computer from 2016 to make all of this. Now, did it produce results that sound decent? Well, maybe not. I think that needs some work. The music isn't really structured or coherent, and you see that in basically all the things I've generated here. That's kind of unfortunate. However, it does replicate the musical textures very well, which is, I think, pretty cool, and it's a really good step in the right direction. And lastly, I wanted to share my results with people, and I think I did that pretty well too. For one thing, I'm doing an Epic Week talk about it, but also I have a notebook on Kaggle that's also in my slides here, where I share the code in a basic outline for kind of how I do this. And you can train on GTZAN using Kaggle's compute for free right now if you use that link. So yeah, just to recap, looking back at the beginning, I wanted to teach an AI to make music using just raw audio and be able to do it on consumer hardware. I ended up developing a process for training neural networks to do just that. I tried a bunch of different kinds of machine learning models. I showed you 2 types. We trained them on a bunch of different genres of music and a bunch of different artists, and even on some voice from YouTube videos. And it learned to replicate musical textures, but it lacked structure. And of course, I'm not done yet. I'm going to keep working on this project, but I do want to open up some questions if anybody has any. I see a lot of different kinds of comments. And yeah, aside from that, if anybody wants, I can I have some additional material. Some questions that are popping in. All right, let me see. Okay. Is there a way to take a musical note sheet and turn that into numbers to get the longer song format? That's a really good question, Brian. The tricky thing with the training process for diffusion is it's really hard to instill the structure as well, because you're really just training the model to say, well, what noise was added to this? And that's kind of it. So there's a bit of trickery there. I've started to sort of try to add structural constraints to the model. I haven't put in the big time on the GPU yet, but we'll see how it goes. I don't think it's going to go super great, but we'll see. Josh Dykeman has asked me, have you thought about trying to separate things like vocals, instrumentals, and tempo? I have thought about the idea of kind of splitting the tracks into each of the different channels, but the thing is you need the stems for that, and it's really, really hard to gather a lot of data for doing that unless you're ripping Guitar Hero, which I'm pretty sure is illegal. Don't do that. Or maybe asking someone for it, I don't know. And then Tristan said, I assume you can't really analyze transients from spectrograms. You want to DM me? I actually don't know what you mean there, but I'd love to learn. I'm still learning a lot. I started this project knowing nothing about audio, and I will say there's still a lot for me to learn. Ethan said, would training the data for longer than 2 hours be possible? Yes, Ethan, actually these last couple models I trained for about a day. So yeah, I did. Okay, I'll actually point out how long some of these were trained for. So yeah, this one was trained for 2 hours. These ones were trained for I think more like 12-ish hours, and the Metallica one was trained for a couple days. These all took a couple days. That's sort of where my iteration loop now is, a couple days on my one GPU. So I haven't really capped there. I've tried training for longer, but I have to be honest, it converges pretty quickly. It usually converges within 100 full steps over the entire data set. So at that point, your gains don't really show much more anymore, which is just kind of unfortunate. Mahavishnu Orchestra. I'm gonna have to look them up. Thanks for the recommendation, Ben. Did you make any attempts to learn to compose MIDI instead? No, I didn't. I specifically chose not to because you can take whatever language model you want to do that. And I thought it's just like simply too easy. And I wanted to give the model like full control over the sonic space rather than like limiting it down to whatever MIDI instrument you ever use. Inputs that are less random. I wonder if you can make an existing song more jazzy. That is something I really would like to do, is sort of like do a style transfer kind of thing. Actually, I'm gonna hop into my appendix just to kind of show you how I would go about doing that. So you can, once you have this diffusion model, you can sort of like hack it to, basically you give it noise and it generates music from the noise. But what if I want to find out like what noise generates this music? Well, you can do that if you run this crazy bunch of code that I have down here, which is not the cleanest thing in the world. But you can do that. You can cheat. You can find what noise creates two things of music, and then you can try to like interpolate between the two. And then you can kind of do like style transfer that way. I found that it seems like my models are a little underdetermined, which means they're too small. And the stuff in the middle doesn't really sound like anything. But in theory, doing this process, the latent space of the model does become like meaningful with a large enough one. 9 Inch Nails has made stems available. That's interesting. That's really good to know. That's very cool. But yeah, and so like I said, there are some links in here. I actually have a presentation I've done internally on diffusion models to the machine learning models team if you guys want to dig more into the math on that. I have a music generation demo notebook if you guys want to see that. There's the data sets. Free Music Archive, by the way, I did try training on that. It took me a long time, but the music was way too varied and the model wasn't producing anything that sounded good. So I omitted that from this presentation. I also have links to MP3Net website, OpenAI Jukebox. Also, just so you know, the sampling is just under real time. So each of my AI Talica tracks that I have on SoundCloud, they're 11 minutes long. They took about 15 minutes to generate, which is quite a bit faster than Jukebox. And yeah, last thing I'll say is you'll notice that like some of these samples are longer than others. Now, a lot of ones I showed you here are, basically like 20 seconds, whatever. All of these examples, they're just one spectrogram's worth. I was trying with like different sizes of spectrograms and stuff, which is why some of them are different length than each other. But you'll notice like this AI Talica thing that I kind of linked to is 11 minutes. And you're probably wondering how I did that. Basically, I take some noise, I generate music from it, and then I like shift the last half to the beginning, fill in the back half with new noise, continue the music from that by filling in that last half of noise, and I keep iterating on that. In theory, it keeps the structure of the music, or it tries to continue, but as we've seen, not too great. It doesn't really do the structure very well. I also, when I was doing a dry run of this, I got some feedback to maybe try an approach where you basically train the model to like fill in noise. So it has like context of some of the music, you can fill in the noise. And then the generation task becomes more kind of like a traditional language model, which is very interesting to me. I started training that on CPU, which is what I tend to do when I'm running something else on the GPU. That's looking maybe promising. I'll find out tonight, actually. And that's another thing that I'm continuing on. But yeah, thank you all for coming. And for your 45 minutes of time. I hope you enjoyed this. I hope this was really entertaining. This was so much fun. I literally spent 2 years working on it. I'm still not done. But yeah, thank you all.